Hello everyone, so my name is Oberlercher. I'm proud to present our latest research result at CM21. The research content is additive manufacturing of continuous carbon fiber reinforced polyamide 6, the effect of process parameters on the microstructure and mechanical properties. The agenda is, at first a short introduction about myself and also about the research content. The second, the material what we worked in this project. Third and fourth are the methods and the results, and at least the conclusion and the outlook. My name is Oberlercher. I studied mechanical engineering, especially lightweight construction. Currently I make my PhD at Graz University of Technology at the Institution of Material Science Joining and Forming, the IMAT. And I work as a junior researcher at Carinthia University of Applied Science at the research group Admire. Yeah, let's start with the introduction about the research content. And first we made a research about the market of additive manufacturing of continuous carbon fibers. And yeah, so Markforged is one of the first who are commercialized 3D printing of continuous reinforced fibers, and he's market leader and own a number of patents of this technology. So they work with pre-pack extrusion or toe pack extrusion, and the toe pack input is heated and extruded without any additional material. So they work with a material bundle with matrix material, so it's a thermoplastic material, and in this matrix are the reinforced fiber distributed. In this picture you see the printer head from Markforged. So one nozzle is for the fused filament, so it's just only used for support material and infill material, and the second is for the continuous fiber printing. So in our research we used only this nozzle. We also analyzed the laminate of this printing technology. So you see here in this microscope image 3 layers, and yeah, it shows some imperfections, how it appears imperfections. So it's a kind of deconsolidation in the mesostructure. So there are appearing some cavities, so this black holes, and also irregular distribution of the fibers in the matrix. Yeah, these imperfections lead to a reduction of the mechanical properties, and therefore this kind of high performance material cannot use its full potential. How can appear this deconsolidation or this relaxation after the printing process? So it is an indicator of poor process parameter selection or inadequate in situ consolidation. How we can reduce this deconsolidation? Yeah, with increasing of the consolidation pressure on the laminate during the heating phase over the time. So you can see it here in this graph, the consolidation process, the whole consolidation process. So it consists of 4 phases: the heating phase, the porosity reduction, crystallization phase, and the cool down phase. So in this 4 phases, it is important to have the correct process parameters over the time. So with this strategy, you can reduce the cavities inside and enhance the material properties. So in this research work, the consolidation process coupled with other defined process parameters is investigated. So the big aim of this strategy is to reduce the cavities content in the laminate and improve the material properties. So for this purpose, the additive manufacturing technology as well as the pre-pack material from Markforged were used. Yeah, in this research we used the Markforged toe pack filament. But before we worked with it, it was something important to know. The fibers are carbon fibers. The matrix are nylon PR6 material. The diameter is about 400 micrometers. We have 1000 fibers in the cross section. After thermogrammetric analysis, we determined a fiber volume fracture about 35%. After differential scanning calorimetry, have a melting temperature about 225 degrees and a glass transmission temperature about 54 degrees. For first analysis of the consolidation of 3D printed continuous fibers, we used the Mark Forged technology. So a Mark I 3D printer, and but we made there some improvements. For the Z-axis, we used a special thread rod for better resolution. We also used a controller board to control the process parameters, because Mark Forged work with the Eiger software, and the Eiger software is a kind of black box, so there it isn't possible to control printing speed or layer height or any else. We also used open source software for control the printer. We control it with the Repetier host, and the slicer software we used the Anisoprint slicer. Yeah, the consolidation was controlled with the nozzle tip, and we reduced the layer height and give with the reduction of the layer height a higher pressure on the printed filament. Yeah, let's come to the printing condition with this printer. So we made there a first experiment with 4 different variations. In every variation we reduced the layer height. For variation A from 0.235 millimeters to D 0.105 millimeters. The printing speed is about 50 millimeters per second, nozzle tip temperature 242 degrees, and printer bed about 30 Celsius degrees. The pictures below, you see there one line, so we printed one line in X direction and made there a microscopy image about and analyzed the microstructure. You see there at sample A very high content of cavities inside, and also the fibers are not well distributed in the matrix. Probe or sample D and C, yeah, it's a much lower content of cavities and the fibers are better distributed inside, and sample D show, yeah, the best results, so a pretty low content of cavities inside, but yeah, the fibers are not well distributed in the matrix material. Next, we produced some 3-point bending test samples, some of 0 degree fiber direction, some for 90 degree fiber direction, from every test sample from A to D. And yeah, sample D showed us the best bending properties. So the bending strength was about 343 megapascal and the bending modulus about 34 gigapascal. It was a big improvement from sample A to D, so you see that the bending strength, so we could increase about 44%, and also in the bending modulus about 25%. In the 90 degree fiber direction, also sample D showed the best bending properties, so the strength was about 26 megapascal and the modulus about 1.4 gigapascal. An improvement from A to B in the strength about 26%, and in the modulus also from A to B about 43%. We also made a microscopic cross-section about sample D. It showed us the same picture as the Mark Forged delivered, a high content of imperfections, and yeah, it is an indication of insufficient heat transfer into the material, and yeah, this still reduced the mechanical properties. For first comparison with the conventional consolidation of 3D printing continuous fiber composites, so with the Markforged technology, a self-developed 3D consolidation printer system was constructed. With this printer head, we are able to have a controlled consolidation pressure, also temperature and time to consolidate. We also made some improvements, so we also implemented a controller board to control the process parameters, same as with the Markforged printer, and we also implemented a load cell who measure the detailed consolidation force. With this 3D consolidation printer, we made two different experiments. First experiments with three different variations, so we also reduced the layer height, so therefore we increased the consolidation pressure from variation A to 2 Newton, B to 2.7 Newton, and variation C to 4.2 Newton. The printing speed was about 50 millimeters per second, the nozzle tip temperature about 242 Celsius degrees, and the consolidation unit temperature about 220 Celsius degrees. In the second experiment, we also reduced the layer height, but also reduced the printing speed. So with this experiment, we made analysis about the heat transfer into the material, and after that have a closer look about the microstructure, especially on the bonding zone of the printed laminate. Here you can see the results of the first experiment. Sample A show a good distributed fibers in the matrix, but yeah, the layer height over the width of this one single line are not really constant. Sample B, the fibers are good distributed and a low content of cavities, and the layer height are constant over the width. And the best result show sample D with the highest consolidation pressure. So the fibers are very good distributed in the matrix, so a pretty low content of cavities inside, and also the layer height is pretty constant over the width. Here you can see the results of the second experiment. So also with the reduction of the layer height and reduction of the printing speed. The first sample with the 50 millimeter per second, so a high content of cavities inside, especially from the first layer to the second layer. A better result with 10 millimeters per second, and the best result with the 0.05 millimeters per second. So the fibers are pretty good distributed inside, so a low content of cavities from the first layer to the second layer, and also the lines from line to line are good connected. Let's come to the conclusion and the outlook. With the Markforged 3D printing system, with the adapted process parameters, we have shown that we can achieve improvement of the mechanical properties and of the microstructure, but it still appears cavities between the layers, and this reduce the mechanical properties. With the 3D consolidation printing system, we had a significant improvement of the fiber distribution and the bonding of the individual layers. And with the reduction of the printing speed, the heat transfer into the material was much higher, and this leads to a reduction of the cavities between the layers. For the next step, we also would make bending tests and determine the bending properties about the 3D consolidation printed material. And in future, the goal is to develop our own consolidation model. So with initial calculations based on different consolidation models, therefore must be performed. And with the first results tests, we will carry it out, and the results are compared with the theoretical values, so with this model. So several iterations will be necessary to optimize the microstructure and the mechanical properties of the material. So this iteration loops, the consolidation model will be revised, and the individual parameters like pressure, temperature, speed will be optimized with this strategy. Yeah, thank you for your attention, and if you have some questions, tell me or write me an email. Thank you very much.